Hi everyone, today I'm going to be going over the AP Physics 1 FRQs which were recently released, the 2026 version. And in this video I'm just going to go over FRQ number 1, and I hope to upload 2, 3, and 4 later on. So all this is unimportant except for this one, the time suggested. It suggests that you spend 25 minutes on question 1 and 3, 30 minutes on question 2, and 20 minutes on question 4. So for today we need to try to finish it in less than 35 minutes to be good on the AP exam. So let's just start with the question. And by the way, this is version J, which is the only one they released. There were like 4 versions, but they only released version J. But anyways, so the water exits the nozzle of a fountain at an angle theta above the horizontal, which is shown here. At time t equals 0, the droplet of water, so one droplet of water, exits the nozzle and follows the path shown in figure 1. So this line, this quadratic, it's just showing us the path that the droplet takes after it leaves the nozzle. And it reaches a maximum height h1. So its max height is right here, h1, at its max, above the nozzle. So at time t equals tf, the droplet returns to the same height at which the droplet exited the nozzle. So we know that right here, it's t equals 0. Right here, it's t equals tf. Let's just say tf. So part A, it's asking us, on the axes shown in figure 2, sketch graphs of the horizontal and vertical components of the velocity of the water droplets as a function of time from t equals 0 to t equals f. So we're going to draw the graph of a velocity time graph for the horizontal and vertical components. So we draw them separately from t equals 0 to t equals f. So from the time that the water leaves the nozzle to the time it returns to the same height. So we know that this is projectile motion. So in projectile motion, after it leaves the nozzle or whatever it is launched from, the only acceleration upon it is gravity, which is going down. And we can call it negative because they chose our directions. Y up is positive and right is positive. So the only acceleration is being put on is on the vertical velocity. So vertical velocity is going to change. Horizontal velocity, there's no acceleration on it. There's no horizontal acceleration. So it's going to remain the same. So it doesn't matter where you draw it, but for the horizontal velocity, it has to be a straight line starting from 0 and going all the way to tf. If you stop short, you might lose points because it says from t equals 0 to t equals tf. And yeah, it could be all the way down here if you want, or it could be up here. It doesn't matter because they didn't give us any numbers or anything, and even the axes are not even marked. For the vertical velocity, the way I like to think about it is, I know that acceleration is constant, and since the slope of velocity is acceleration, I know my slope has to be constant, and I know my slope is negative g, right? So my slope is negative g, so it's going to be a negative linear line. So it could start anywhere here. All that matters is that it continues to tf, like this. And they're not going to grade you on this, but technically the area under the graph here and the area under the graph here should be equal. But basically, so if we look at the graph just to explain it, you start with your maximum velocity for the vertical, and then you approach 0. When you approach 0, that is when you get to this h1 at the maximum height. Your vertical velocity is, vertical velocity, that's right. Vertical velocity component is 0. And then after that, after it reaches that, acceleration starts to speed it up again. So initially it's slowing it down, and then you reach the maximum, you reach 0 for a moment, and then you start speeding up because gravity is on your way, which is why it starts speeding up in the negative direction. So that is it for part A, for part AI, and this would give you all points. Whoa, oops, my bad, this way. So the next part AI2, tells you to derive an expression for the speed of the water exiting the nozzle. Express your final answer in terms of theta and h1 and physical constants. So our physical constants are most likely going to be like g or something if needed, as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so I just took a moment to bring these equations in because these are the only equations that are relevant right now because it's projectile motion. So we're going to be using the kinematic equations, which only work when acceleration is constant, which acceleration is. So right now I can see that this last equation, it relates everything I have. I have velocity, the acceleration, and the change in x, which we're going to be using change in y, because we're going to change it. We're going to be looking at the vertical component. So looking here, Oops, my bad. So looking here, if we want the velocity of it as it comes out, we see that there's a sine angle. So we can't just get the vertical component or the horizontal component because that won't be showing it because it's coming out at an angle theta. So if we can imagine the two components here, so we had this x component for velocity, vx, like that, and then you have this vertical component. The actual the actual velocity is going to be like this. So if we want to use the vertical component to be able to get this velocity, so the hypotenuse basically, we're going to have to use sine theta. And now that sine theta is equal to opposite over hypotenuse, so that would be Vy, the y component velocity, over V0, which is just the velocity in general. So when we use the equations for velocity, we're going to be plugging in sine theta V0, because that is equal to Vy, if that makes sense. Because this will enable us to have it in terms, we will have an equation with V0, which we can then solve for to be able to find what V0 is. So using this, we're going to use this equation, knowing that Vy is equal to V0 sine theta. V0 sine theta. Another important thing to note, we have to choose what times, because we have, right here, we have V initial squared and V final squared. V initial, we already know, it's when the water exits the nozzle. It's what we're trying to find, which we're going to be substituting this in for. And then the other one is V final, which it says Vx squared. It's basically the final velocity. So what I'm going to do, I'm going to take the final velocity as it being right up here at the maximum height, because it makes it easier, because right here the vertical velocity is 0. So solving in terms of vertical velocity, like using the equation with vertical velocity, Vy, is going to help me, because then the left side is going to be 0, making it a lot easier. So what the equation is going to be now is, let me zoom in, Vy squared equals V 0y squared plus 2a delta y. So like I said, V final, we're going to take it at the max height. So V final is going to be 0. 0 squared is 0. So it's just 0. So then we get 0 is equal to V0y. So V initial y, we're going to substitute that for V0 sine theta, because we want to solve for V0. So we need to somehow get it into the equation. So V0 sine theta, and that whole term is squared. Plus 2a, we know that a is g, so a, we're going to put negative because it is negative g. And then delta y, it was shown to us in the diagram that it is h1. So 2, negative g, h1. Now we're just going to solve for v0. So I'm going to start by just trying to separate it. So let's just get it out of the parentheses. So we get v0 squared, and then sine theta squared, plus 2 negative g h1. And by now we've done all the hard work. Now it's just simple algebra, and it's equal to 0. Let's remember that. So now I'm just going to isolate the term. So I get negative v0 squared sine theta squared is equal to negative 2g h1. And then I see there's 2 negatives, so that can cancel. Those are gone. And then now I'm just going to isolate v. So I'm going to start by dividing both sides by sine theta. Let's just divide the whole equation by sine theta squared. So I'm left with v0 squared is equal to 2g h1 over sine theta squared. And the last step is just taking the square root of both sides, which would eliminate this. And then we get v0 is equal to the square root of 2g times h1, all divided by sine theta squared. So that is how you do this part. Okay, so I deleted everything except for our final answer, so that we can work on the next part. So part A3 says the nozzle has a circular cross section. So circular, it's a circle cross section with a radius r. Derive an expression for the volume flow rate of the water. So volume flow rate, we have to remember, because not explicitly stated, but you can find it in the equation sheet still technically. Volume flow rate, which is sometimes shown as Q, or for this I'll just put, yeah, I'll put Q because I don't want to use V again. Q is equal to A times V, and A is the cross-sectional area, which is why they gave us the cross-sectional radius, and that it has a circular cross-section. So, derive an expression for the volume flow rate of the water exiting the nozzle. Express your final answer in terms of theta, H1, R0, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So this is a fundamental physics principle, which is what we're going to be using. So to derive an expression for the volume flow rate, we need to find the circular cross-section of the nozzle, of where it's leaving from, where the fluid is leaving from, and then V, which is velocity, the exit velocity. I might have said volume before, I'm not sure. V is the exit velocity. So we know that it is a circular cross-section, so it's going to be a circle with radius r. This radius is r. So even if you don't know this, it's going to be on the first page of your reference booklet. But the area of a circle, which is going to be the area of our cross-section, is pi r squared. So it's going to be pi. Let me zoom in. That looks better. It's going to be pi. And then r, where do they label at? Because we have to make sure we use their symbols. R0. R0 squared. And then velocity, we can't use velocity because that's not given here. We can use pi h1r. But remember, in part A2, we already solved for velocity, which was square root 2gh1 sine theta. H we can use, theta we can use, g is a constant, so it's all good. So pi r squared times the square root of 2gh1 over sine theta. I'm not sure if I made this clear, but it's sine, the theta isn't squared, it's sine theta squared. I did not make it clear over here. So it's sine and then theta squared. Sine theta squared. Yeah, so this would be equal to the volume flow rate. It's very simple. You just have to know what volume flow rate is, and that is equal to AV. Because on the equation booklet, they do give you the equation A1 V1 equals A2 V2. So this is just a conservation of the flow rate, but you have to know what it is, because if you just look at this, you won't be able to know, oh, this is the flow rate. So that's something you need to know for the AP exam. And so then the last part B, the fountain nozzle is replaced with a new nozzle with a radius smaller than r theta. So the exit surface area where the nozzle is, it's got smaller. The water exits the new nozzle at the same angle, so same angle above the horizontal. The volume flow rate of the water exiting the new nozzle is equal to the volume flow rate of the water exiting the original nozzle. Like I said, it's conserved. What's going to ask? A water droplet exiting the new nozzle reaches a maximum height h2 above the nozzle. Indicate whether h2 is greater than, less than, or equal to h1 by writing one of the following. So we can look back at our equation, and also we have to indicate that we have to justify our answer, including qualitative reasoning beyond mathematical derivations. We can use mathematical derivation or expressions, but we have to explain it with words, like write a couple sentences. Okay, so based on this equation, we are told, we know that this is conserved, so this has to stay the same between the original nozzle and this new nozzle, which has a small radius. But here, radius goes down. So if radius goes down, if we want, let's consider these two different terms. We're going to consider this a left term, and this is the right term. So if this term goes down because radius goes down, g is the same, theta is the same. Because of that, if r is going down, so this whole term is going to be a smaller number, this term has to be a bigger number. And because g is conserved, 2 is a constant, theta is conserved, so everything is conserved except for h. H is going to have to increase in order to counteract the decrease in radius, in order to keep Q, our volume flow rate, the same thing. So we're going to indicate that H2 has to be greater than H1. And then I'm just giving you a moment to write it. So there are two ways, there are more than one way to answer this question. So the one I said before I added this text is that in part B we found that Q is equal to this thing, power squared 2gh1 sine theta squared. And based on this equation, if radius decreases, h has to increase if the volume flow rate is to remain the same. But I feel like this might not have enough qualitative reasoning beyond mathematical derivation or expressions. So more reliable and more possibly a better answer would be to say, based on the equation a1v1 equals a2v2, which is in the equation sheet, we know that velocity increases because originally the radius was higher, so in a2 radius is smaller, so the surface area, the cross-sectional area becomes smaller, which therefore velocity has to increase. And then we say, because velocity increases, that means the vertical component of velocity also increases, and a greater vertical component of velocity would result in a greater vertical distance traveled, and therefore h2 is greater than h1. So you see how in this one, it's a bit better because we have an equation, but there's a lot of qualitative reasoning as well. So it's just a safer option to choose if you're trying to get all your points. Exam, it is also fine if you go over, since maybe you're better at a different, like they gave you 30 minutes on the experimental, maybe you're good at the experimental, so you shouldn't like be. So yeah, that is it for FRQ number 1. If you have any questions, please let me know. If I made any mistakes, please let me know, because I'm just a student who took this class just like you guys. So and yeah, thank you for watching.